my name is Dana Golden, and today we're going to talk about congestion games. Congestion game is a type of game where multiple players share a set of resources, and each player's payoff depends on the level of congestion on each resource. So think about two commuters choosing between two routes, or you think about many commuters choosing between two routes, route A and route B, to reach their destination. Depending on how many commuters choose each route, the commute times can either be longer or shorter. I'd like to point out right now we're looking at Governor Kathy Hochul's put in place congestion pricing in order to place a cost on congestion. This is because congestion is an externality. I think what's really cool about these games is that they give us a systematic way to think about interaction amongst many players. And this is something you notice in the real world. You notice that sometimes adding a road doesn't necessarily reduce congestion. That's a very cool thing. So in terms of the cost functions, you have a cost for one route. Here you have CA equals 10 plus 2XA, where XA is the number of commuters choosing route A, and you have CB, cost of route B equals 15 plus XB, where XB is the number of commuters choosing route B. In our class, we're always going to assume that XA and XB are fractions. Always assume that this is the proportion out of 1. So each commuter wants to minimize their travel time by choosing the less congested route. So how do you solve the congestion game? You have to find the Nash equilibrium condition. So in equilibrium, the travel times on the routes have to be equal. Otherwise, commuters would switch to the route with a shorter travel time. So I want you to remember this. This is an important thing. In game theory 1, if all players are ex ante identical, if all players have identical characteristics at the start of the game and there's no randomness, all characters have to have the same payoff at the end of the game, because players, we assume, are rational and can choose to do whatever benefits them. So in equilibrium, the travel times should be equal because all players are ex ante identical, and because otherwise commuters will just switch to the route with a shorter travel time. So think of this as an arbitrage condition. So equilibrium calculation, let the total number of commuters be n equals 10. Suppose XA commuters choose route A, and XB equals n minus XA commuters choose route B. So you set the costs equal to each other. You set 10 plus 2XA equals 15 plus n minus XA, and then you solve for XA. So 3XA equals 5 plus n. XA equals 5 plus n divided by 3. And then n equals 10, and we find XA equals 5, XB equals 5. You could also have used 0.5 and 0.5. As a Nash equilibrium, 5 commuters choose route A and 5 commuters choose route B. Both routes have the same cost, so no consumer has an incentive to switch. So you want to balance across resources, leading to no incentive to deviate. So here is another example of a congestion game. So here we can, again, in this case, X are proportions. So we have two possible routes. We have 3x plus 5, and we have 7 plus 2x. So in this case, this is actually 3x1 plus 5 equals 7 plus 2x2. So you remember, because these are two different proportions, and then x1 plus x2 equals 1. So once again, that's 3x1 plus 5 equals 7 plus 2x2, and x1 plus x2 equals 1. So what you solve this is you do 1 minus x1 equals x2, and then you plug that in that formula for x2. 3 times 1 minus, or sorry, 3x1 plus 5 equals 7 plus 2, 3, 2 times 1 minus x2, x1. So 3x1 plus 5 equals 7 plus 2 minus 2x1 equals 3x1 plus 5. And then you get 9 minus x1 equals 3x1 plus 5. 6 equals, 4 equals 4x1. x1 equals 1. So the interesting thing here is that we have x1 equals 1, so we've proven that all consumers are going to go SW, WT. That's just the standard route everyone is going to choose. Now let's add in this WV. So now CX0, X equals 0, so now you go directly SW straight to WV without any cost, and then to VT. So now, because 2 times 1 is equal to 2, you will never go WT because this will always be shorter even if everyone travels here. So now the new route is 3 plus 2 equals 1. And so everyone saved a little bit of time. So in this case, the superhighway led to a lower congestion. But that's not always going to be the case. I think on your homework, I've given you an example where this is not the case, and actually the superhighway will lead to more congestion. So just keep in mind, adding this road can be helpful. In this case, we went from everyone having to pay 3 and then everyone had to pay 5, so a total of 8. Oh, sorry. Yeah, for a total of 8 to everyone having to pay 3 and then 2 for a total of 5. And then now we have another congestion game where we have, again, x1 squared and x2 squared. So I'm not going to solve this one today, but 1 plus x1 squared equals 2 plus x2 squared. And then x1 plus x2 equals 1. So that's how you solve congestion games. Again, going through this, basically what you want to do is you want to add the other x1 and x2 to get 1. And then you want to set the costs equal to each other. And I'll see you next time. I'll leave it there, and I hope you have a great day.